In 1960, Chrysler introduced a lighting system for their Imperial passenger cars they called panelescent dashboards. The gauges were backlit by a strange, continuous glow. This material produced no heat like a standard tungsten incandescent bulb, and it didn't rely on electrified gas trapped inside rigid glass tubes like a neon sign. It also operated differently from light-emitting diodes. An LED is a highly directional, intense point of light generated by a semiconductor junction. The dashboard glow, by contrast, was perfectly flat. It was cold to the touch, and could be shaped into flexible ribbons or wide panels, emitting a uniform 360-degree surface glow. This is electroluminescence, the Destrio effect. To understand how it produces light without heat or gas tubes, we have to dismantle a strand and look at its physical layers. If we take a standard strand of electroluminescent, or EL wire, and strip away the outer plastic sheath, we expose the primary structure. That flexible outer casing simply protects the components and dictates the unlit color of the wire. The solid copper core sitting in the center acts as the main electrical highway. Between that core and the outer sheath are two hidden layers. The copper is coated in a paste called a phosphor. Wrapped tightly around the outside of that paste are two microscopic angel hair wires. In this cross-section, the inner copper core and outer angel hair wires are separated entirely by phosphor paste. They never touch, acting as a capacitor. Applying voltage accelerates electrons through the phosphor. They collide with metal centers, emitting photons via electron impact. Since the light is generated by an electric field passing broadly through a continuous phosphor paste rather than a single point, the wire emits a perfectly even, seamless light across its entire surface. But if we want to turn this wire on, we run into a strict electrical constraint. If you hook this wire directly to a standard set of AA batteries, providing direct current, the wire will flash exactly once and then go completely dark. Applying DC power instantly charges the capacitor. Once both sides reach capacity, electron flow hits a dead stop. No light. To keep it glowing, you must constantly flip the polarity. Supplying alternating current forces the capacitor to charge and discharge continuously. This requires a piece of hardware called an inverter, which transforms the low-voltage DC from your batteries into a high-voltage AC signal. The inverter switches that polarity thousands of times a second, vibrating the components and generating the trademark high-pitched whine of EL devices. Understanding this delicate capacitive balance dictates exactly how you handle the wire. Bending it too sharply will break those fragile angel hair wires, shorting out the capacitor. And if you string too much wire onto a small inverter, the voltage drops, causing the entire strand to fade. This flat sandwich structure of electrodes and phosphor doesn't have to be wrapped into a wire. It can be manufactured as flexible tapes and incredibly wide flat panels. Modern LED and LCD screens require complex active matrix circuitry at every single pixel to function. An EL panel operates with a fraction of the complexity, requiring only those basic flat layers of electrodes and phosphor to glow uniformly. That structural simplicity yields extreme reliability. In environments where low power draw and fail-proof illumination were required, engineers utilized electroluminescence. It even lit up the instrument panels inside the Apollo spacecraft. That same flat panel reliability was eventually miniaturized for the mass market, providing the gentle, even backlighting found behind the screens of liquid crystal digital watches and pagers. Now, the technology is moving into soft robotics with hyper-elastic light-emitting capacitors, or HLECs. By replacing the rigid glass and metal layers with stretchable hydrogel electrodes and elastomers, engineers can deform the light source entirely, stretching it to more than 4 times its original size while it continues to glow. By treating light as a flexible, physical material, rather than trapping it inside a glass bulb or a rigid diode, electroluminescence proves that the geometry of a light source can be just as functional as its brightness.